1965, a computer scientist named Tony Hoare added a single feature to a programming language. He later called it his billion-dollar mistake. That feature was null. Today, null references are responsible for the majority of runtime crashes across every major programming language. A null pointer exception in Java. Segmentation fault in C, a type error in Python. The cause is almost always the same. Your code tried to use a reference that points to nothing. In this video, we are going to understand exactly why null crashes programs, how it propagates through a codebase, and what modern languages are doing to make null impossible. Your program runs on memory. Every variable that holds an object is really holding a pointer, a memory address that says where the object lives. Normal pointer contains something like 0x7FFE20A1, a real address where a real user object sits in RAM. A null pointer contains 0. Address 0. An address 0 does not belong to your program. The operating system reserves it specifically so that any attempt to read or write there immediately triggers a protection fault. When your program dereferences a null pointer, it is literally asking the CPU to go fetch data from an address that does not exist. The CPU raises an exception. The OS kills your process. That is a null dereference crash. Every language has a different name for it, but they all have one. Here is the exact sequence of events when you dereference null. First, the CPU reads the pointer variable and gets the value 0. Second, the CPU tries to read memory at address 0 to find the object fields. Third, the memory management unit sees that address 0 is in a protected page, raises a hardware exception, and the operating system immediately terminates your process with a segmentation fault, a null pointer exception, or an access violation depending on your platform. There is no recovery. The process is dead. This is why a single missing null check can take down an entire server, crash a mobile app, or corrupt a database right mid-transaction. Null failures come in two flavors, and the second one is far more dangerous than the first. The first is the immediate crash. Your code dereferences null, the CPU fires, the stack trace points directly to the offending line, and you fix it. Painful but straightforward. The second flavor is silent corruption. Your code checks for null and silently skips an operation when it finds one. The user was supposed to receive a notification. The payment was supposed to be recorded. The cache entry was supposed to be written. None of it happened because somewhere upstream a function returned null instead of a real object, and the caller quietly did nothing. These bugs can hide for weeks. The crash, when it finally comes, is nowhere near the original null. The traditional fix is the null check. Before you use a reference, you check whether it is null first. This works when you remember to do it. The problem is that null checks do not compose. Every time a function might return null, every single call site needs its own check. Miss one and you have a latent crash waiting in production. Over time, a large codebase accumulates hundreds or thousands of null checks. They crowd out the actual business logic. They make code harder to read, and they still do not catch every path because null is contagious. A function that receives a null and passes it downstream has now made every downstream caller responsible for a check they did not know they needed. The fundamental problem with null is that it is invisible to the type system. A variable of type user and a variable of type user that might be null look identical. The compiler cannot tell them apart, so it cannot warn you when you forget the check. The solution is to make absence visible at the type level using a wrapper called option or maybe. Option has exactly two states, some which contains a real value and none which explicitly represents absence. The critical difference is that the compiler now knows the type is option of user, not just user. You cannot call methods on an option directly. You are forced to pattern match or unwrap it, which means the compiler physically prevents you from forgetting the null check. The check is not optional, it is part of using the type. Modern languages are eliminating null entirely at the design level. Rust has no null. Absence is represented by option, and the compiler enforces that every option is handled before you can access the inner value. Dart and Kotlin use null safety, where variables are non-nullable by default and you have to explicitly opt in to nullable types using a question mark suffix. The compiler tracks nullability through the entire type system and rejects code that might dereference a null without a prior check. Swift has optional with built-in syntax for safe chaining. Even Java and C# have retrofitted optional and nullable annotations respectively, though these are weaker because they are not enforced by the compiler across the whole language. If you are writing in a language that still has null, there are concrete steps you can take right now. First, annotate every method parameter and return type with @non-null or @nullable and turn on your static analysis tool. It will flag unguarded dereferences at compile time. Second, use objects. Require non-null at the top of any method that must not receive null. This makes your program fail loud and close to the source rather than silently propagate null through 5 layers. Third, never return null from a collection method. Return an empty list. Return optional, empty. Fourth, treat null as a design smell. If you find yourself returning null to indicate absence, consider whether a dedicated empty state object or a result type would communicate intent more clearly. Null is a shortcut that always costs more than it saves. Tony Hoare called null his billion-dollar mistake not because null itself is a bad idea, but because making it invisible to the type system was. Every language that came after has had to pay that debt in crashes, in corrupted state, in hours of debugging. The good news is that the industry has largely solved this problem. Rust, Kotlin, Swift, and Dart have shown that you can have a systems language or a practical production language with no null dereferences by design. If you are starting a new project today, choose a language that enforces null safety at the type level. If you are maintaining existing code, use annotations, use static analysis, and retire null returns one function at a time. Thanks for watching. Tony Hoare called null his billion-dollar mistake not because null itself is wrong, but because making absence invisible to the type system was wrong. The good news is that modern languages have solved this. Rust, Kotlin, Swift, and Dart enforce null safety by design. If you are starting a new project, choose one of them. If you are maintaining existing code, annotate, use static analysis, and retire null returns one function at a time. Null is a debt that compounds. Start paying it down today. Thanks for watching.